Okay.
A very good afternoon, everyone. A very good afternoon, everyone. I welcome you all for the next session for the third day of the FDP program, organized by IQAC Om Sterling Global University, Hisar, Haryana, in collaboration with Vaish College, Bhiwani, Haryana, on quality and technological enhancement in teaching and research. The next session is on probability methods, and the resource person for the session is Professor Rishi Pal, HOD, CSC, Guru Jambeshwar University, Hisar. But before that, I would just like to give a brief introduction of Sir. Professor Rishipal Singh, Department of Computer Science and Technology, Guru Jambeshwar University of Science and Technology, Hisar. In his 26 years of teaching experience, he has 82 publications in international journals and conferences and has guided 10 PhD scholars successfully. Currently, he has 8 scholars registered. Thank you so much, sir, for visiting us here today. I'm handing over the mic. Please give a big round of applause. Before the session starts, जो हमारा OSGU का ओम स्टर्लिंग ग्लोबल यूनिवर्सिटी का एक रिवाज है, हम जो हमारे गेस्ट्स होते हैं, जो हमारे रिसोर्स पर्सन होते हैं, उनको एक प्लांट दे के सम्मानित करते हैं. सो आई वुड लाइक टू रिक्वेस्ट आवर डिग्नेटरीज, Mohinder Punia sir, our VC sir and PVC sir, and the resource person to please come on the stage and do the proceeding. And ladies and gentlemen, please put a big round of applause. Ladies and gentlemen, Professor Rishi Palsi.
Good afternoon, everybody. Good afternoon, everybody. Today we are going to discuss a topic which is quite interesting and useful in research, particularly when we are doing research in wireless networks. This area of probability models is required while dealing with protocols or any other electric signal, etc., on the physical layer. As we know, in the networks, there are layers. Okay, so physical layer, then medium access control layer, and even up to routing layer, these probability models are mostly used. And this is not only in the wireless network, it may be used in other research areas like data mining or pattern matching. Wherever it is there, you can apply it. Okay, so let me start with the. Do we have job? Thank you. जो ठीक लगे. Probability models. Here, I am assuming that you know the basics of the probability, right? And all of you, since you are from engineering background, So you must have read it into +1 and +2. That much is required as a basic. Today we are going to discuss a basic block of probability models that is called random variable. A random variable is a real valued function, and mind you, we generally represent it with these notations: capital X, capital Y, capital Z, generally. Okay. And on the point of view of definition, as I am saying it, real valued function. So this is the definition of random variable. When we are assigning values from the real numbers, okay, capital R is set of real numbers, right? This is sample space. When we are assigning values from real numbers to the sample space, that particular thing is called random variable. Okay. For example, we are tossing 4 coins, right? Number of coins are 4. Now I am defining the random variable y that there is at least one head is there. Okay. So tossing 4 coins, we can have what will be the value to y? 1, 2, 3, and 4. Okay. So here this particular thing, tossing 4 coins, is an experiment, and this variable which we are defining, that at least there is one head, is random variable. Okay. If I am saying that y is equal to 1, y is equal to 2, y is equal to 3, and y is equal to 4. Let us take one more example. That we are flipping 2 dice. Okay. And we are defining random variable x as sum of numbers which are coming to the dice, right? Then we can say that it will have values as x is equal to 2. Okay, because what will be the sample space? 4, 5, 6 on one dice, and it will be the on second dice, right? Sum will be from minimum will be 2, then you will get 3, then it will be 4, 5, and so on, right? It will move on up to 12, right? What will be our sample space to compute the probability? That is 36, right? And here some this favorable sample space or outcome or event for this x is equal to 2 will be only 1, means 1 on the first dice and 1 on the second dice. So it comes out to be, the probability of this comes out to be 1 upon 36. Similarly, here you can see it will be 1, 2 and 2, 1, right? So it comes out to be 2 by 36, right? So on, and you can compute it 1, 3, 2, 2, and 3 comma 1. So this definition here, where we are assigning real values to sample space, okay, to each outcome of the sample space, is called random variable. Depending upon the type of sample space, these random variables can be classified in two types: discrete and continuous. Okay, so it is totally dependent upon sample space. If sample space is finite, then the random variable is called discrete. Okay, if it is infinite, or we can say it is continuous, continuum, uncountable, then the random variable will be called continuous. Okay, so let me start it from the discrete one, right? So we are going to discuss discrete random variable. As I have told you, depending upon the sample space, we are classifying it. So here, the most important concept is probability mass function, which we call it short PMF. Okay, it will be defined as probability for random variable when it is attaining the value of A in the sample space. Okay, similarly, when we were talking about for sum of the dice, then it was whether it is x is equal to 2, x is equal to 3, like that. Okay, so for these values, whatever is the probability at that particular moment, this will be called probability mass function, right? For this one, it was 2 by 36. For x is equal to 3. Fine. So now, next concept, important concept is that summation of this probability mass function for all whole given sample space should be equal to 1, as this is the concept of probability, okay, which was flipped by Kolmogorov, right? So summation of this probability mass function should be equal to 1 in each and every case. For example, we were taking 4-coin example, right? And we were saying that if it is y is equal to 1 out of 4, so this sample space will be head, okay, head, tail, like this. So how much combination will be there? 16. Okay, so similarly, we can find out the favorable events and compute the probability. In the end, the summation will be equal to 1, right? Now, we will discuss types of discrete random variables. You might have studied about it. Number one is Bernoulli. This is the basic one. Okay, when we are going for any trial, single trial, right? There are only two possibilities. One is failure, another one is success. If we assume that the probability of success is P, then the probability of failure will be definitely 1 minus P, because the summation of probability mass function has to be equal to 1. Okay, so this is basic random variable. Now let us move to the next one. Which is quite interesting. It is binomial random. See, when there are n number of events, right, and n number of independent events, each and every event is independent, okay, not dependent upon the outcome of the previous or the next event. Now, out of this n, if I number of events are for success, then how much will be the failure? N minus I. Number of outcomes will be failure, right? Then you see, out of this I number of success, then we define a random variable x, which is indicating the number of successful outcomes. Here the x which we are representing as random variable, it is representing, if I am saying x is equal to I, then I number of successful outcomes. Fine. Then we can say that probability mass function PMF for binomial random variable will be x is equal to I and Ci, okay, I number of combinations out of n, right? P is probability of success, Pi, and since P is the probability of success, so 1 minus P will be probability of failure. So this is the probability mass function for binomial distribution. Okay. Now, if we look for the application of this particular random variable in computer science, right, then we can assume a problem. We can assume a problem that suppose in networks, right, it is wired network, okay, or we can call it a LAN, local area network, right? There are probability P of working a node successfully, right? and 1 minus p will be probability of failure, right? And we are given 4 nodes in one network and 2 nodes in the another network. You can assume it is a LAN 1 or it is a LAN 2. Then I am putting one condition that the network will work if at least 50% of the nodes are in working condition. Okay, then we have to find out that what will be the probability that this 4 node network will supersede the 2 node network in the working. Got the problem? हम ये पता करना चाह रहे हैं कि 4 नोड वाले नेटवर्क की क्या सक्सेसफुल प्रोबेबिलिटी होगी जो कि 2 वाले से अच्छा बेटर काम करेगा. ओके, तो now you see here this 50% condition is there. So out of 4, all 4 may work, 3 and 2. These are the 3 possible outcomes. चारों नोड काम कर रहे हैं, only 3 or minimum 2, because at least 50% condition is there. Similarly here it will be 2 and 1. Now we can find out the probability based upon this probability mass function which I have already told you. For the first case, 4, it will be 4C4 p raised to 4 1 minus p raised to power 0. Isn't it? Plus 4C3 p raised to power 3 1 minus p raised to power 1. Plus 4C2 1 minus p. Right? This is the possible summation of probability mass functions for this case. What will be for this one? It will be 2C2 plus 2C1 right? What we have to find out? We have to simply say, put the greater than equal to symbol here and then try to find out the solution of this equation. It will be a polynomial equation in terms of p. ठीक है, निकाल लोगे, algebraic equation आएगा. Okay, so this is the application of binomial distribution in wired network, which I am showing you with the help of example, right? Next one is geometric random variable. See, we have one channel for transmission of data, and we have divided it into equal number of slots. Okay, size of slot is equal. And there are n number of nodes which are competing with each other to reserve a slot. Right? You have gone through the CDMA protocol, okay, slotted aloha protocol, right? Here, a node is trying for the reservation until it succeeds. It will fail in the first trial. It will try in the second. If it will fail in second, it will try up to third, fourth, fifth, up to the n number of trials until it is successful in reserving the slot. Okay, this particular phenomena represents this geometrical random variable. For example, we are denoting it by capital X. Okay, this is trial up to the success. Okay, so what will be the probability mass function for this one? If there are n number of trials, क्या रहेगा 1 minus p n minus 1 into p, isn't it? n minus 1 तक फेल होगा तभी तो n में ट्राई करेगा ना सक्सेस के लिए, है ना? Now you can find out the condition which I have told you, that summation of probability mass function for all trials should be equal to 1. ठीक है, निकाल लेंगे हम इसको. कैसे निकालेंगे? Summation n is equal to 1 to infinity p 1 minus p n minus 1. So p is not dependent upon n, so it's a constant value. We will take it out. N is equal to 1 to infinity 1 minus p n minus 1. Right? It is infinite geometric series. Okay, and so we know summation of infinite geometric series is equal to where a is less than equal to 1. So we'll put the value of a here 1 minus p, right? So it will be p into 1 upon p, which comes out to be 1. Okay, so we can say that this probability mass function for the geometric distribution is correct. You got this application? Wherever there is trial in the last success, we can apply this geometric random variable. Next one is very quite interesting and very powerful as well. Poisson random variable. Okay, this random variable is defined in terms of probability mass function for a given constant value whose value is greater than 0. Okay, and we are saying that we will define it, the probability mass function for this random variable x for the given value I. It will be e raised to power minus lambda I factorial. Whenever, for example, this is the room for us, okay, and this is our space area for any wireless network establishment. Okay, since I'm from the area of networks, so I can give you example of networks only. Okay, and we are looking for deployment of nodes here, right? For that randomness, we will use this Poisson random variable. Okay, and this lambda will become area. For example, we are assuming that it is a circular region, then this lambda will be equal to pi r square. Okay, and then we can find out that how much number of nodes we are deploying in the particular given area. Okay, similarly we can look out for this square or rectangle, whatever it is. We know the formulas. Okay. More probably, this Poisson distribution leads us for the queuing theory. Okay, that is another concept, right? We will discuss the connection later on if time will permit. Here, again, I am telling you that we can find out that the summation of probability mass function is equal to 1. Fine. If I am saying that on a given highway, for example, this NH number 52, which is there in front of your institute, right? In one side, with distribution lambda is equal to 3, with the given value of lambda is equal to 3, what will be the probability that on a given day no accident occurs? Zero accident. In case of zero accident, I becomes 0, isn't it? So it will be the random variable value is 0. Therefore, it comes out to be e raised to power minus 3, 3 raised to power 0, 0 factorial. So it will be 1 upon e cube. We know the value of e. It is somewhere around 2 point something, between 2 and 3, right? We can compute the whatever is the result there. Okay. If I am saying it is more realistic approach that no accident occurs, for the worst case I am saying at least one accident occurs. In that case, it will be 1 minus x is equal to 0, because summation of all events will be equal to 1, right? So we'll minus the value of no accident, right? It is very, very important random variable. Let me tell you, from the point of view of wireless networks, I found it very interesting. Whosoever is working in the area of wireless network should focus on it and the further application of this distribution, right? Because rather than with queuing theory, it leads us to the stochastic process also, which we are going to discuss definitely. Okay. These are the 4 discrete random variables. Now we'll talk about continuous random. I have told you that when sample space S is continuous or continuum, then the random variables are called continuous. Here, any probability of x is equal to b or something like that, we can compute it based upon these formulas. You see, in case of discrete random variable, there was the concept of summation. Here, in case of continuous random variable, we are going for the integration, because integration represents I mean values. Here, this fx is called probability density function. बैकअप नहीं है क्या राइट सर?
यूपीएस का है सर, ऑनलाइन पे चलता है।
अच्छा. Okay. So this is called PDF in short. Okay. Similarly, as it was in the case of PMF, if we are going for this in sample space from minus infinity to infinity, then fx dx will be equal to 1 always. Okay. There is one more concept which is there, that is called cumulative distribution function. Which is called CDF. Okay, this will be for up to a particular certain value. Okay, if I am saying that for x is equal to a, then this CDF for f will be equal to capital F will be equal to integration from minus infinity to a fx dx. Okay, and vice versa is also true. We know that differentiation and integrations are complement to each other. So for the computation of fa, means we can compute probability density function from the cumulative distribution function with the differentiation of fa. Okay. So now we will move to the types of continuous random variable, as we have done in the case of discrete one.
Sir, any function for the limit minus infinity to plus infinity exists. Can you tell me any function fx equal to?
No. See, this I am telling you, these are the limits which will exceed from minus infinity to plus infinity. Function is probability density function.
Yeah.
Okay.
So can you tell me the value of fx for these limit exists?
Sir, whatever function we will put here, we will compute for this range. It is not, I am telling you that real valued functions or real values range from here to here. It is not necessary that always we have to apply these limits. I'll tell you the example. Just give me one more minute. We are talking about, I'll give you your answer. Uniform random variable. This is the first random variable for the case of continuous, right? Here I am saying fx will have value of 1 or 0. Okay, when it will have value of 1, when it is lying between 0 and 1. Fine. In this case, what we will do? We put value of limits from 0 to 1.
But a function in the form of e to the power something that will exist.
Sir, not always. Not always. I'll come to that point also. Not always. There are functions, okay, which are minus infinity to infinity plus infinity. Okay, trigonometrical functions are also there, right? But here, in this case, which I am going to tell you, it will be not the case that we will put the values for the function from minus infinity to plus infinity. It will depend upon the function. Okay, it will depend upon the random variable which we are going to discuss, right? If, for example, I am not taking this value 0 to 1, I am taking it to a to b. In that case, what will be this? It it comes out to be b minus a. Okay, outcome. Then we can say that uniform random variable, if we are putting it for the limit from alpha to beta, it will be in this form. Got it? Why? Because the integration of this PDF within the limits should be equal to 1. Okay? Will it be 1 here? होगा या नहीं होगा? Next one is exponential random variable. The PDF for this random variable will be lambda e raised to power minus lambda x for all value of x which are greater than 0. Okay, for rest of the values it will be, now you see it, sir, this is exponential function, but the limits will carry from 0 onward, 0 to infinity, isn't it?
The function uniform e to the power minus x square. For this function, the two limits are minus infinity to plus infinity. Right, like this one. There is only one function which is e to the power minus x square.
Sir, let me tell you very categorically. I am a man of computer science. I have gone through this mathematics just for the application to the wireless networks. Okay, I mean, not that much expert that I'm going to teach you functions or relations or जितना मुझे पढ़ना होता है उतना पढ़
It's
लिया.
a more mathematical.
Yeah, that is more. It is also mathematical, but I am telling you why, because mathematics, without mathematics, we cannot do the research. Let me tell you very clearly. Whichever is the area, the simplest area is data mining. There also you will find out that many kernels are using exponential functions. Okay. Now we can also compute here CDF and all those things here. Okay, CDF for this one. How will compute? 0 to a. Okay, lambda e raised to power minus lambda x dx. ठीक है, इंटीग्रेशन कर ही लेंगे इस फंक्शन का. This particular random variable is very useful wherever we have to apply the concept of memoryless system. Means we are not dependent upon the past. Okay, there it is very useful to apply that we can apply this exponential random variable. There are many random variables which are continuous in nature. One of such kind is Weibull. Okay, and it is used in design of the software testing because it is directly related to the failure rate. Okay, therefore, if the people or the person who is looking for the research in software engineering, he or she can cancel this particular distribution. Why would? There are other distribution also, gamma distribution, but I am going to discuss next one, which is quite interesting and useful also. Normal random variable. Whenever you come across any such bell-shaped diagram, okay, and we are fitting our data in this bell maximum data, such type of random variables are called normal random variables, which are distributed with reference to the mean value of the data. Okay, and this is it depends, the shape of the bell depends upon the variance. Okay, if variance is low, the shape of the bell will be like this. If variance is high, then the shape of this bell will be like this. Okay, so the distribution function, probability distribution function for this normal distribution will be like it is 1 upon sigma root 2 pi e raised to power minus x minus mu upon root 2 sigma square, and the value of x is from minus infinity to plus infinity. Here it is, sir. मुझे उस टाइम एग्जांपल नहीं याद आया. Okay, so you were also correct. हाँ, normal distribution. Okay, it is used heavily in many areas. Okay, particularly in data mining, where we have to collect the data and classify it on a particular pattern, right? And then put it on this. There you will see that this normal random variable or normal distribution is quite useful. Okay. Let me. So far we have gone through the classification of random variables, which was discrete and continuous. Next thing is expected value of random variable. Again, in case of discrete, the expected value, which we represent it like this, e raised to power x, will be summation x px. For example, we are throwing a dice and we have this sample space. The probability for each one, okay, will be 1 by 6. How to compute expected value for this experiment? This we can compute. Ex will be equal to 1 into 1 by 6. 1 here, then the probability of that particular value. 2, 1 by 6. 3 into 1 by 6 plus 4 into 1 by 6 5 into 1 by 6 and 6 into 1 by 6. Right? So we can take 1 by 6 as common. 1 plus 2 plus 3. कितना हो जाएगा summation?
यहाँ 1 नहीं होएगा.
It will be 13, 18, 11, 15, 18, 21. 21 by 6, that is 7 by 2. Got it? Similarly, we can find out the expected value for the given discrete random variables. Okay? For the continuous one, it will be expected value will be x fx dx. Okay, we'll multiply that value with the probability density function, and then we can compute the expected value or the mean value for the given experiment. Okay. For example, we are looking for uniform random variable which was distributed like 1 upon beta minus alpha for the value of x lying between alpha and beta and 0 otherwise. If we are looking for the expected value for this particular random variable, continuous random variable, then it will be like integration from alpha to beta. The function is beta minus alpha dx. Sorry. Yes, dx. Okay. Now we can compute it. It will be, let us take this value out, 1 minus beta minus alpha, and it will be x beta alpha. So beta minus alpha it is 1. Okay. Similarly, for other random variables, we can compute it. Along with this, there is one more concept which is called stochastic process. Okay. थोड़ा सा लेते हैं. Stochastic process. We have discussed random variables when a given random variable is indexed for a particular parameter, then that process is called stochastic process. And the most important concept which we apply in research for this stochastic process is Markov chain. Markov chain states that if we divide, this is past, today, and it is future. Markov chain states that future is not dependent upon past. It is totally dependent upon today. Okay? Tomorrow is not dependent upon yesterday. It is totally dependent upon today. And this property, particular property, leads to the very, very easy modeling of the complex systems as well. Okay, I can give you examples again from wireless network. It is heavily used in the modeling of IEEE 802.11b. Okay, on other wireless fidelity models. Technologies, right? Sorry, not model. In the technologies, it is heavily used. Okay, you can go and search papers on wireless network with Markov chain. You will find out many papers. Okay, so you got the connection. Stochastic process is a process which is collection of random variables indexed on a certain parameter. Maybe it is time or something else, right? Maybe it is temperature. Okay. Then again we are moving from here to Markov chain. Markov chain totally removes whatever was there in the past. Okay, it is totally dependent upon current situation. Okay, so we have many things, but it will be too heavy. That's all for today, and you can. I'm ready to. Actually, it was quite mathematical, and there were lot many symbols. Therefore, I have not used these PPTs. So that my heart is breaking. But I think. Any query? I hope you may have got something out of it. Thank you.
Thank you so much, sir. Thank you so much for the methodologically sound session. So, the first half of the session ends here today. And now I would like to request our dignitaries, Dr. Mahendra Punya, sir, and our Pro Vice Chancellor, sir, to please come on the stage and felicitate our resource person for the day. I would also request Benda, sir, to come on the stage. It is the certificate of appreciation for today's resource person, Professor Rishi Pal Singh from Department of Computer Science and Engineering, Guru Jambheshwar University of Science and Technology, Hisar. Ladies and gentlemen, please put a big round of applause. Thank you so much, sir.
Next session.
So today's the first session for the third day of the MDP session ends here, and the next session will be on 2:30 p.m. today. That will be on research methodologies and publication ethics by Dr. Rajeshwar Pal, Professor, Swami Vivekananda Subharati University, Meerut. Thank you for your participation. Thank you so much.
Thank you.